Hi everyone, and welcome in this second part of the journey we started on the SDL and WebGPU introduction in Emscripten. If you missed the first part, I suggest you have a look at this one first because we were discussing the setup of the environment with SDL and Emscripten at the same time. But now in the second part, we're going to be focusing on what I call the step 3 and 4 in the initial plan. So this will be covering the introduction of the WebGPU framework, first in a simple native application, and then we're going to extend that to also support compilation with Emscripten. So let's get started. Now, step number 3, which is the SDL application using WebGPU, but building only with the native compiler. We again have only two files, so the CMake file and the main file, but the main file here is a bit larger than the previous test applications. In the CMake file, the application we're going to build is called test SDL WebGPU, and then in the configuration file to execute this test SDL WebGPU app, I have this script. So we can give it a try just right now, and that's the result that we will get. An SDL window with some content here rendered with WebGPU. We cannot resize this window, in fact. Probably need some additional flags to do that, but it's a really minimal test, so that's all we need for the moment. We see here that we are inside the main loop, and if I close the window, we are going to exit the application and everything seems to be okay. Now for the construction of this app, I was mainly using this as a reference implementation. If you go on this page, you will get some pretty cool instruction on how you can build this application, which is going to run as a native application or as an Emscripten build Wasm module. And I basically started with following those indications. So starting with an empty main function and preparing an executable and so on. Then concerning the down library, that's where I was actually drifting a little bit from the suggestion that is provided here, because I'm really building my down libraries myself, so not really as part of the project. In fact, when I'm building as a native application, I'm going to include the down include folder and the down link directory, and I'm going to provide those WebGPU libs. And the WebGPU libs are defined one level above this, so in my test folder in this case, and this will provide me with all the down base libraries plus the real down libraries themselves that are needed to access the the standard WebGPU interface from down. In fact, there's another way to use the down library, which is what I'm currently using in the Nerveland engine itself, but this is a bit more intrusive because instead of using this WebGPU down, we're going to use this down proc library and directly accessing some of the function from down. And this is probably something I need to change at some point, and I should really use this version also, but not really relevant to this the current recording. For the down base library, actually we have quite a lot of them, so that's the list. Not sure that all of them are needed here, but this is what you will get produced in the folder where you build down anyway, and I was a bit lazy, so I just provided all of them to ensure that there was no missing link. And anyway, continuing with this reference document, another key difference here is that they are suggesting to use the GLFW library as a windowing library for this example code, but on my side, I decided to go instead with the SDL2 library, which is playing the same role. Then we have a start function that you are going to execute here to produce your window, and then you're going to enter your main loop. Initially, you would get this empty window if you were running your application at this point, but we're going to just bypass this. Then there's a step where you are actually trying to use WebGPU and try to access some of the WebGPU elements. The first thing you need to do is to get access to the WebGPU instance, and then you need to get your device, and you cannot really get that immediately. So the way you are supposed to do it is to provide a callback that will be executed once the device is ready and available. So you will get this device as an argument of your callback. And the function which is implemented here will do everything you need to request a device and all. And at some point in the end, it's going to execute the callback. So now your main function is something like that. You retrieve the instance, then you try to get your device, providing a callback which will store the device as a global object in this case, and only after that you start your actual rendering loop. Once you have a valid device, you can start considering what to do next to actually render something on screen, and the next step would be to prepare your swap chain. So the start function is slightly modified here because you need to create a surface, and that's where you actually need a windowing library, GLFW in this case, but SDL2 in our case. Then this init graphics is going to take the surface and produce a swap chain from it, and after that you enter your render loop. And also, when you have control of the render loop, you are responsible for calling this, the instance process events method. If you don't call that, then well, there's not much that's going to happen on the WebGPU side. So again, this is all good, but the render function here is still empty, so you're not really going to render anything on your surface. That's the next step, and first you actually need to prepare a render pipeline. I'm going pretty quickly on this because that's not really the topic of the recording here, but you really need to provide those elements anyway if you want to do anything with WebGPU. And to prepare the render pipeline, then you need a shader code. You need some kind of shader to do the rendering. Here you see that it's a very simple shader. You have the vertex shader here, which is using the vertex index, and depending on the index value, so you see you have the position, which is an array. The first index here is 0 in X and 1 in Y, so that the top center vertex of your triangle. Then you have -1, that's the bottom left vertex of the triangle, and then you have 1 in X and -1 in Y, so that's the right bottom vertex of the triangle. And depending of the index you're receiving here, you will select the first or the second or the third position, and that's directly a position in the clip space, so you can provide that directly as your output value. And for the color, we are simply going to output a red color, so you get a red triangle in the end. To build the render pipeline, you need a few additional structures, and you will provide the module. And as far as I remember, this was not really working for me. I'm not quite sure what the version of this code, but we'll get to the actual source code in a moment. And so at the end, you should be able to produce your pipeline object. And that's finally when you can populate the render function. You prepare your color attachment. So you prepare a render path using this color attachment, so you're going to render to the swaption current texture. You then prepare a command encoder, which is going to render to this render path using this pipeline and drawing 3 triangles. And there's nothing to bind, nothing to provide as additional buffer or anything. Everything is simply provided here in the vertex shader. Finally, you produce the command buffer and you submit this command buffer, which should give you this kind of display. So let's see what we have done ourselves. So we start at the bottom with the main function, again, this section here is really not relevant. We create the instance, which is exactly the same thing as what is done in the reference article. Then we have this get device function, and we are going to retrieve the device with a final callback, and we're going to store this device. The first thing which is different on my side is that I decided to also provide those additional helper function to get some output details from the device. So you have this set and capture error callback, which is pointing to print device error. This method will simply print some error message in case there is a device error received, and it's basically the same for those two additional callbacks here. So that's a device lost callback or the device log callback. And next we reach the call to the run function. In the run function, we start with the initialization of the SDL library, the creation of the window as before. Then we create a surface for this SDL window. So this part is not really similar to what is provided in the reference article, because as I said, we're using SDL instead of the GLFW library. And so for the create surface for window, we're going to get first a surface descriptor, and then we're going to create the surface from the surface descriptor. This part is really what is available already from the WGPU library. So all you really need to figure out is what is done here in this get surface descriptor, and this one is going to return a pointer on the chain struct, and this chain struct is where you will put the information concerning your window. And to do that, you first need to get the window information from SDL to populate this structure. Then if you're on Windows, this should really be Windows flag, and you're going to retrieve the handle from your window as a structure element here, and also the instance for that window. Otherwise, if you are on Linux, you should proceed a bit differently. If you're using the X11 server, then you're going to get a display from this structure here and the window number also. And on Mac, you should again proceed differently, but I don't have any Mac, so I didn't bother to provide support for that yet. So that's it for the creation of the surface, which should get you to this point. Then you can initialize your graphics with the surface. In the init graphics, we're going to create a swap chain. This part is similar to what is done in the article. And then you create the render pipeline, which again should be mostly similar to the article, except that you actually have a problem with the shader code that was provided, because if you remember, here we have the shader code definition, and we're only going to provide the code here, and that's apparently all what is needed. But you in fact really need to specify what is the entry point, at least. Initially I was not providing the entry point myself, and that would lead you to a crash in fact, and you would not be able to generate your pipeline, which means that for the current version of Down, at least, this is the correct way of defining your shaders. When you're done with the graphics initialization, you enter the main loop. So while this main loop is running, you will retrieve all the events. You may eventually quit the application, and otherwise you will render your frame, present that frame, and process any pending events from Down. The render frame function again is exactly the same thing as what is provided in the reference paper. Another thing which I forgot, which is also slightly different from what is mentioned for the render pipeline construction, is this line, or in fact those two lines. I'm also specifying here that I would like to retrieve the compilation information in case there was an error in the shader. And if you want to see the output from this callback, you actually need to call process events. And that callback is defined just before, taking the compilation status, compilation info, and you may display some of those messages, if any. And I think this is it now concerning the overview of the code For the building part, you see that the name of the application is test SDL WebGPU. As before, I have a dedicated script to execute this application, NVL SDL WebGPU. And if we run this application, you get the triangle like that. Concerning the CMake build instructions, again, this part here is not really relevant because this application is not meant to be built with Emscripten. Only those 3 lines here are relevant for us, and there is really not much more. Linking to SDL library, and this is it. Finally, let's move to the final test application, the test WebGPU Wasm, which is very similar to the previous one, except that this time you can build the application either with your native compiler or also with the Emscripten compiler. Let's see what is actually different in there. First, let's have a look at also the article itself, because the first part of that article described the native compilation, and then it's going to provide some additional details on how you're going to set up the Emscripten compilation. So you see that you definitely need some updates in your CMakes. You really need this flag when you're building with Emscripten, so we'll get to this one, or this one also when you want to use this library in Emscripten, but that's not our case. We are going to provide use SDL flag, but we already mentioned that in the previous test application. So you need to figure out whether you're building with Emscripten or not. In this case, they suggest to provide directly an HTML file, but I'm rather just producing the GS file myself. And we're going to provide those flags a bit differently. Then when it comes to the code itself, you will need to provide access to the Emscripten header file. So that's something we will also include in our code. And for the surface generation, we're not going to use SDL directly here. But anyway, that's how we're going to do it. And after that, this is something we already mentioned. You cannot really assume that you will keep the control on your main loop when you're building with Emscripten. Instead, you need to provide a render function, and this one is going to do the rendering for you. What we can also notice here is that the render function that we're executing is what we were executing in the native code here. So it means we're just bypassing any event polling from your windowing library. We're also bypassing the swaption present operation or the instance process events operation. So we'll get a bit more in this in a moment. And after that, that's basically all you really need to be able to build your application with Emscripten. And then they are trying to execute that with a mechanism which is not really what I'm using myself. So let's have a look at what we have now. So our main function, as before, we create the instance, we get the device, and first difference compared to the previous native only implementation, when you are using Emscripten, you don't have access to those two functions, but this one here is available. Next, we move to the run function, and here I'm creating the window, but the window is used only here. I'm wondering what would happen if I was not creating this window at all. But anyway, we see that for the surface creation, this is exactly the same thing as what is mentioned in the article. So we're going to retrieve this canvas element. And if we look at the HTML code corresponding to this test application, you really see that we have a canvas with the IDE canvas. After that, we reach the init graphics, but in this one, there is nothing changed compared to the native implementation. And then, if you are on Emscripten, you just call this Emscripten set main loop to execute the render function. One thing which is slightly different in the render function, we'll get back to this part in a moment, but something which is different for both the native and the Emscripten version is that now I'm trying to change the clear color here for the render pass to at least get something to change dynamically to ensure that I'm really displaying multiple frames and not just a single frame in my test application. So this is just going to take simulated time value, which I'm simply incrementing every time render is called, and this is used to change the clear color. Then you do the rendering as before, and this is it basically. So when building this application with the native compiler, I can then use this NVL WebGPU Wasm script to display the native application like that. And at the same time, when I build with the Emscripten compiler, I can then use this script here to call this HTTPS server to serve this folder to display the Wasm module application. So you see here that this is rendering the canvas just as initially expected. One additional note on this is that I can resize the window and the canvas is going to be resized accordingly. And in fact, you can, in this case, display some of the outputs, and you see that you have a message here, canvas resize, and it's going to be updated continuously. And this is in fact coming from the Emscripten application itself. So let's have a look at that. This is the part of the render function which I have not mentioned yet. So in case we are building with Emscripten, we can retrieve the size of our target object, which is canvas, and we can figure out if this is different from the current size, and in this case we will display a message indicating that the canvas was resized. Technically, when you get an event like that, you would I think try to destroy your current swap chain and build another one. But this is a bit tricky with a WebGPU, so I thought that maybe it was not really a good idea to push it further for this simple demonstration. And anyway, you may also not really need to do that if you go with a dynamic viewport, so yeah, maybe something to consider if you really need to, but maybe not also. And in fact, also here in the HTML file, if you want to resize the canvas dynamically, you really need to specify that the dimension should be changed to 100% in a simple CSS style block. Okay, a final thing that we should mention is that, as you can see here, the application is running in Chrome, while the previous Wasm application was running with Firefox. And the reason for that is that if you try to use Firefox to run a Wasm application with WebGPU content, then it's simply not going to work. In fact, this is something I can try again, maybe here. If I remove the Chrome flag, this is going to behave in a similar way to what we have here, because by default, when I call this without Chrome, it's using Firefox for the execution. And now if I try to execute this again, it's opening Firefox, but you get nothing displayed. And why that? That's because you simply don't have WebGPU adapter in Firefox at all. I thought I had another message for that. Get device, blah 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 blah. Well, I guess no. But yes, if you try to check if you have the WebGPU available in Firefox, it was going to tell you no. Actually, you could go on this web page, for instance, which is meant to test if you have a WebGPU available, and on Firefox you will get this kind of error message. Navigator GPU is undefined. Whereas if you try something else like WebGL2, then the loading, should work eventually, and you get this display. And of course, as you might expect, if you use Chrome to go on the same page, then you can display the content with a WebGPU and you get no error message. So that's the reason why we really need to use Chrome to test development of those WebGPU Wasm modules. But now this also brings you to another consideration. It's not really a concern for the development of your WebGPU application in itself, but just in case this could be of interest, you have to know that when you're using the Firefox browser to test your module here with this HTTPS server module, then the mechanism in place is going to stop your server and execute that until you close your page. So if I run, for instance, the SDL application, here I start the application, it's opening the Firefox web page, and you see that yes, the server is running. And if I close this page, it's going to stop everything properly. This is not working just out of the box when you're using Chrome to execute your Wasm module. I tried a few different things like new window, incognito, and I don't know, whatever. But the point is, with Chrome, you're going to share your process with the other running Chrome processes, which means that the mechanism here will be confused and it's not going to be able to close the application directly. The solution to this is that you need to specify a random or at least temporary folder for your user data directory when you execute Chrome. And in this case, you will get a dedicated process for this Chrome page. And when you close the page, then it's going to close the process properly. So that's really an interesting feature that you need to keep in mind. And well, this is it, guys, concerning this overview on how you can build this minimal test application both as a Wasm module and a native application. As a final note, maybe, I have also extended my Nervlian Adventure repository, so now we have this additional folder for the experiment number 3, and in there you will find the source code for the test application that we have described in this recording. The first one here is a minimal one, native version. Here is a Wasm version for SDL. Then that step 3, SDL with WebGPU. And the final one here, which is the one that you can build as a native application or as a Wasm module also. Alright guys, so this is it for this time. I hope you learned something and you found this session interesting. As usual, if you have any question, just let me know in the comments and I do what I can to try to provide more details. And also, if you like this kind of content, don't forget to subscribe, of course. And in any case, I'll see you next time for the next recording. Meanwhile, happy coding on your side and see you next time. Bye bye.